New stuff. New stuff. And it's an inflection point, calculus, in the course because we're going to start using calculators a lot more. Okay? So from now on, you need to use your calculator because there's going to be some things. I don't know why I'm putting on quotes. There are going to be some things that our calculator will be able to do that we just won't be able to do. Okay, and that's not like arithmetic. Well, it kind of is, but so bring your calculators from now on, and we are going to talk about displacement. Now, the definition of displacement is like how far the dude's going to end up versus where he started. Okay. And the key to this lesson is that there's two ways to calculate displacement. There's two ways to calculate what we'll see as, for the first question, a distance. Okay, so here's the first problem that hopefully will show you the two ways to calculate like the distance. In this case, the distance and the displacement are the same, but we're going to see how distance and displacement is going to change, and we'll just stick with displacement. Okay, so the answer to this question is 140 miles. What's the two ways you can get 140? If you have your calculator, whatever, you can use it, but like you don't need to. Get 140 different ways. I had to get away from you kids. I drove on I-35 with a velocity of 70 miles per hour for 1 to 3 hours. Travel from a mile marker, a position of 234 to a mile marker, 374. Get 140 two different ways. Go. Tell your neighbors how you got the 140 two different ways. Go. Good. You're probably familiar, maybe from middle school, maybe from like physics, the whole like distance equals rate times time, right? The whole velocity times time gives us how far we've traveled. And I could do 70 times 2, and I got 140. But I also realized that I can have position. I can have my position, my ending position, and I can subtract my starting position. And this is when I did the 374 minus the 234, and I get the same answer, 104. My friends, two different ways to get the same answer. Now we are going to focus our attention on the left side first, and how you can visualize this 140 coming from 70 times 2. If I give you the graph of velocity, what does 70 times 2 look like here? It's a tough question. You might not see it. But then I'm going to give you the answer, and you're like, all right, I got it. Very good. If you looked at the area, all of these velocities are constant. It's 70 miles per hour. Area under my velocity curve shows me the whole velocity times time. Now I'm going to use the word area a lot starting from now. But I'm also going to use the word the accumulation of my velocity. If I like accumulate all these velocities, I get my area. my area, v times t, gets this 140. Cool? All right. Now, same type of question. And we still have two ways to calculate the answer. But one of the ways is going to be incredibly difficult to do by hand. The other way we'll be able to do no problem. Okay? So now I'm traveling in a rocket-propelled car. Velocity is changing. We are accelerating. So velocity is 3t squared. And I'm actually not going to give you any position. I'm just going to give you a velocity function. And I'm going to ask, how far did I travel over 4 seconds? Okay? So again, there's two ways to calculate this. I could take my velocity times my time, or I could take my position at time 5 minus my position at time 1. Now, what's going to be hard to do? It seems like both. But this v times t is tough. Because in the previous situation, my velocity was a constant 70 miles per hour. I could do 70 times 2 and I got 140. Is my velocity constant here? No. My velocity is changing. But if I accumulated all of these velocities, and if I had a lot of time on my hands and did these velocities times like the moments and times in which we're at those velocities and add them up and kind of like get that area, boom, I'd be able to get that v times t. Okay? But right now, I don't have that time. So this half of things right now, I don't know what to do with. But let's see if we can do the other half of things. Let's find some x function. What would be x of t if v of t is 3t squared? Good. We know that you take the antiderivative of v and you get x. Now, the problem is I have a plus c, and I did not give you an initial position. I did not give you any position to plug in to find c. But watch what I can do. If I plug in 5, and if I plug in 1 and subtract them, understanding that this c is not like the c's that we had last unit, or if like you added 2 c's, it's just a different c. This is a number. This is my initial position. So it will be, I don't know, like 5 or 6. So that means this would have to be 6 and this would have to be 6. What happens to the 6's? When you subtract this from this, they go away. So it turns out we don't need to worry about the c because it'll go away. We get 125 minus 1, which is 124. Fantastic. I just got how far I've moved over the 4 hours by hand. But I still don't feel great about it because, like, in the other question, I was able to confirm it. I had 140 equals 140. Well, this is where our calculator is going to come into play. Okay? So, everybody break out your calculator. And everybody reset things. Second plus 712, so we're all in the same boat. Second plus 712. Okay, you with me? I would like you to graph 3t squared, but it's going to be y equals 3x squared, and we're okay with that. Now, hold on. Don't press graph yet. Second plus 712. Okay, now please adjust your window so we can see everything. we're going to go up to a v of 75. So I'd like you to change your y max to be 80. Y min can stay at 0. I'd like you to change your x min to be 0 and your x max to be 6. So we can see the graph as I see it right here. Okay? So x min 0, x max 6. We'll be able to see our velocity curve. -10, probably too much, but whatever, to 80, we'll be able to see all of our velocities in our window. Cool? Now, my calculator can do a lot of arithmetic really quickly. It can accumulate these velocities. It can do a lot of velocities times time. It can get this answer 124 by doing this method v times t. I'm going to show you how you do it. And it's going to look weird because it's like, wait, doesn't this mean something else? Go to second, calc, everybody. Go to number 7. We there? Now that's an integral. It's like, well, integral means antiderivative, but we're going to realize that it's going to mean more than just an antiderivative in a second. We're going to use the notation for 2 different things. Okay? But whatever, just go with me, go to 7. And it says lower limit. Well, it's like, hey, calculator, please do a bunch of velocity times times between 1 and 5. So I'm going to type in 1 and press enter. I'm going to type in 5 and press enter. And look at what my calculator does. It shows you like, hey, hold on, give me a couple seconds. I'm accumulating. I'm doing a bunch of velocity times times, and boom. My calculator just got 124. The same answer that I got. But my calculator didn't do the same thing that I did. I used calculus. I used Newton's discovery that antiderivatives can actually get us areas. Your calculator just found the area. It approximated. It did v times t a bunch of times. I said, oh, I know there's an alternate way. I could take an antiderivative, get a position, subtract positions. The c's won't matter. I'll get a displacement. Boom. Now, what we will do is a process, and I'm going to show you the notation that we will say is this left side of things, okay? And this is so important, they called it the fundamental theorem of calculus. The fundamental theorem of calculus says, hey, there's 2 ways to find displacement. You got velocity times time, which is the area under v, which typically you can only find with a calculator if v is changing. But that equals change in position, which you can find by taking an antiderivative without using a calculator. Okay? And here's what they decided notation was going to be for this accumulation. They said, well, if we could do it by hand, because they didn't have calculators back in the 1600s, if we could do it by hand by taking an antiderivative, let's use this integral, okay? If one way to calculate an area is to take an antiderivative, let's say this left side is using an integral. And it's like, okay, I know I'll have to take the antiderivative, but there's more than that. After I take the antiderivative, I have to do something with it. I have to plug in a and b. So it's like I get, you know, this whole x of t kind of. I get like this x of t plus c. But then I have to plug in the whole b and the whole a. So what they did is they decided, hey, let's put a and b here. And all of a sudden, putting this down makes this notation kind of an integral, but it's called a definite integral. It changes things to be like, hey, This is accumulation now. This is find the area. Under V from A to B. This is what your calculator will do. What you will do if you don't have a calculator is take the antiderivative. Oh, well, that integral kind of helps me show, oh, okay, I can take the antiderivative. I can then, and I'm going to use another line, plug in A and plug in B. This means find the change. And I'll get x of b minus x of a, which is our displacement. And this is what my process would be without a calculator. Just to confirm this, let's go into our home screen. Okay, go into your home screen. Let's get out of this graph. I love the visual of this. It shows you it accumulating. But go into your home screen. Okay, so second quit. Go to math. Go down to 9. Math 9. Remember, n-deriv is how you can use your calculator to approximate a derivative. It uses a slope formula. FNINT means, hey, here's an integral. Now, the integral does mean antiderivative, but like that's just helping you know what to do. Oh, I have to take the antiderivative if I were to do this by hand. But in your calculator, this means accumulate. Accumulate my velocities, which were 3t squared. 3t squared. Accumulate these velocities from 1 to 5. We are used to having to have the dx next to the integral, even though you guys never put it, but it's like everything's in line. Now, your calculator doesn't take an antiderivative. Your calculator does a lot of arithmetic really quickly. But here is that visualization of what you saw in your calculator on the graphing mode, and you press enter and you get that number 124. Okay? Now, it happened really quickly, but your calculator didn't take an antiderivative. That was a beautiful discovery. That allowed mathematicians to find areas without having to do arithmetic. But now that we have a calculator, boom, we can do both. We can do the arithmetic, the accumulation, the velocity times time, or we can do it by hand. Okay. So let's pretend we don't have a calculator. But don't let it go too far. I say there is a particle whose velocity is 3 sine t. And I want you to figure out how far he moved. And again, let's remind ourselves, what is this number 124? What was that number 140? That was like our distance traveled, how far I ended up versus the start. How far the dude is versus where he started. This is displacement. Okay? So, and I didn't ask you any of these questions in the quizzes. I didn't ask you like how far did he travel. Now we're starting to talk about how far he traveled when he traveled left. How far has he traveled over the course of 4 seconds? Here, how far has he traveled over the course of pi seconds? Okay, so I don't have a calculator, but watch what I'm going to do, and this is going to be like a process, and you're not gonna love it. You won't have to have this graph, but it's good to visualize things. You're going to say, oh well, if I had a calculator, I would plug in this. Accumulate my velocity from 0 to pi seconds. This is what I would just plug into my calculator. Yay, I'm done. Don't do it yet. We're pretending we don't have a calculator. Okay? This represents the area. Well, we will find that area using the alternate approach by taking an antiderivative, plugging in the ending position, subtracting the starting position, the whole mile marker idea behind finding displacement. So you start with this, take the antiderivative, right? The integral means antiderivative to you guys right now. So it's like, this is a good reminder. This is why this is used both for accumulation and for antiderivative. I want to find the area. Well, take the antiderivative. I get -3 cos t plus c. I will then plug in 0 and pi. I have more space. I would get -3 cosine pi plus c minus -3 cosine 0 plus c. Since c is our initial position, my c's will cancel. So in reality, we can actually go back and not even worry about it from the start, since I'm subtracting these two positions and I'm just getting my displacement. Cosine of pi is -1 times 3 is +3. Cosine of 0 is 1 times -3 is -3. This is my whole, here's x of t, here's x of pi minus x of 0. You get 6. We just did that by hand. Mathematicians were not able to find the area under a sine curve until they understood about antiderivatives. They found the area under 3 sine t was 6. This is so important, they called it the fundamental theorem of calculus. Derivatives, rates of change; antiderivatives, accumulation, accumulating rates of change, areas. Well, let's just confirm this. We do have a calculator. We do have technology now. We are in the 21st century. Find the accumulation of my velocity. Find my velocity times time. Use your calculator to get this answer 6. You may either go in the home screen and math 9, or you can go and graph it and do second calc, and you'll see that integral. We will get the answer 2 different ways. One way without a calculator, one way with a calculator. So let's graph. Everybody, go with me. 2 ways for our calculator to do the velocity times time. We can either graph 3 sine t. I'm probably going to go back and adjust my window to be from 0 to pi. And I don't need to go from -10 to 80. I could literally go from like -1 to 1. Actually, not to 1, to like 4. There's the graph of 3 sine t. My calculator can accumulate. My calculator can find area because it can do arithmetic very quickly. It will do velocities times like minuscule seconds at which they're at the velocity from 0 to pi. Watch it fill in nicely. It is accumulating. It gets there. We got that answer 2 different ways. Yeah. It's an approximation, but it does such a good job that it ends up being the actual. You will see that there will be some times, depending on the function that we type in, that you will get, similar to when we use our calculator and then derive, 6.00001. That's showing you that your calculator, all it's doing is its best job approximating. Yeah. Yeah. We go back to the beginning to talk about how far do I travel. There's 2 ways to do it. Velocity times time or change in position. Keep that in your brain. Okay? There's 2 different ways. Velocity times time, change in position to find a displacement. Okay? My calculator helps me if velocity is changing, because I can't do velocity times time if velocity is changing. It's going to be too much work. My calculator can do all of these changing velocities times times at which they're at that velocity, like lots of little rectangle kind of things. It can get this. What I can do is find change in position because I know calculus. Okay. Cool. All right. Now, what we had been finding for the first two examples were really distances because my velocity is positive. I'm moving to the right. But we have to understand what happens if velocity changes sign. Okay? So, this situation I can do both ways without a calculator because velocities are going to be constant. So I'm just going to show you. I could do, and I could also find the change in position, but that actually would take longer. So I'm just going to show you what would happen. And let's stick to the velocity times time and not worry about change in position right now. I'll worry about it when it's more applicable. Man traveled right for 4 seconds at 3 meters per second. Here's my velocity curve, it's 3. The man then changed directions, and for 6 seconds, he traveled at a velocity of -5. Okay? What do we see? How can we describe the man's motion? And what would be our answer for like change in position? Well, this area here of 12 is telling me that the dude started somewhere and he moved to the right 12 units. The area under the velocity, and this is very important, the v times t shows me how far I moved in a certain direction or how far I've displaced. And then I got this area here from 4 to 10 of -5, which is -30. What does that tell me? That after he moved to the right 12, he then moved to the left 30. Now, if we combine those two areas, what do we get? -18. 12 plus 30 is -18. Well, -18 would be the change in my position. This -18 stands for how far the dude is at the end from where he started, his displacement. He moved a total of 48 units, but he ended up 18 units to the left of where he started. Okay, it's important to keep that idea of changing direction means displacement tells me how far I ended up versus where I started. And this example will kind of show that. Now, this is another example of, hey, my velocity is changing. So I want to find the displacement from 0 to 3. But if I looked at the graph of t squared minus 4, it'd look like this. Do you have to know that? No, you don't have to know that. You don't have to know that. But what I'm telling you is that there are going to be two ways to calculate my total displacement. Number one, I could use my calculator and I could accumulate my velocities over the 3 seconds. Find the area under the velocity. That would be this negative area, which is telling me how far I moved left, plus this positive area, which is telling me how far I moved to the right. Okay? The other way, which I can do without a calculator, is to do kind of what this is telling me to do. This means accumulation, but it also means to you guys take the antiderivative. Take the antiderivative Plug in 0 and 3, you won't have to worry about the c. I get 9 minus 12, that's x of 3, minus, plug in 0, you get 0. I get negative 3. I just got that by hand, which means my dude at t equals 3 is 3 to the left of where he started at t equals 0. He will move left more than he will move right. This area will tell me how far he moved left. This area will tell me how far I moved right. If I knew when my velocity hit 0, I could, even at a bad time, I could split this up into when I'm negative, when I'm positive. Go ahead and confirm that negative 3 using your calculator. You even just do zoom standard here. You could say, hey, I would like you to accumulate my velocities from 0 to 3. And it shows you all you need. Negative 3, I got the same answer. But my calculator did it a different way. It found that area, it found that area, it added all together, it accumulated all my velocities. Okay, now I want you to skip a little bit. I want you to go to the graph of V. And now what's this mean? You guys know what it means. Dude ended up 3 units from where we started. What we're going to end up doing is really focus on my areas when my velocity is negative and the areas when my velocity is positive. And just be able to find those specific values. Now, our questions, when given the graph of V, will be provided more information. This negative 2, that's the area under V from 0 to 1. This 4, area under V from 1 to 3. This negative 3, this is 1. Tell your neighbors, what does that extra information tell you? Come on, stay with me, guys. When's the particle moving left? When the velocity is negative, right? This is a review question. You would say from 0 to 1 and 3 to 5, right? Guess what? That negative 2 tells me how far I've moved left. It tells me my displacement. This is how far left. So tell me, what's my position at the first second? Telling you the position at the 0 second is 5. What's my position at the first second? 3. How did you get that? I know where I started. I know how far I've moved. Now I know where I am. What's that 4 tell you? How far I've moved right. What if I add up negative 2, 4, negative 3, and 1? Do I get 0? Oh, that sucks. That's funny. Well, what does that tell me? What's my position at 6? What's my position at time 6? 5. How do you get 5? Right. If I move left 2, right 4, left 3, right 1, where do I end up at the 6th second? Back where I started. We don't have to take antiderivatives. You know, you have all the information you need, but now you have to be able to interpret it. It's more. This is new. Okay? Areas under velocities give you displacement. It gives you how much we move. This will be then applied to functions. So weird, like we use f prime, f double prime to help us understand x, v, and a. We're about to, in the future, use x, v, and a to help us more understand f prime and f double prime. That the area under a derivative will tell me how much f is increasing. The same deal. Okay? We could understand all of the motion of my dude. The dude started at a position of 5. Everybody start your dude at a position of 5 at t equals 0. After 2 seconds, he's at a position of 3. Here's my dude. T equals 1. After 1 second, he's at a position of 3. Sorry. After 2 seconds, it's tough to tell. If we split this in half, then maybe we could say it'd be 2 to the right. So you're right, but maybe it's not regular. But you would know that after 2 more seconds, he will be increasing his position by 4. So he would go up to 7. Here I am at t equals 3. And then I end up going to the left 3. I'm going to the left 3. I'm there at t equals 5. And then I pop back to the right 1. I end up back where I started at t equals 6. Okay? Areas under velocities, change in position. Good. Now, we are going to use that same idea to find unknown position. Okay? Go back. We have what we're going to call an old way. An old way of finding positions. This is what you did on your first quiz. What did you do on your first quiz if I gave you a velocity, I gave you a position, and asked you for a position at times 3? Take the antiderivative. Very good. You took the antiderivative. You got 1/3 t cubed plus c. You then plugged in 0. And you got c is 3. You got a nice fancy x of t. You then plugged in 3. And you got 9 plus 3, which is 12. There's a new way. You're going to love this way. Why? Because it's going to use your calculator. If I know a position, and I know that my calculator can find the area under a velocity quickly, could you get that answer 12 a different way? Okay, get it. Try. How'd you know that I ended up back where I started when I gave you the graph of v? Because you know the area of the velocity tells you how much you're moving. You said, oh, I went to 5. Then I went to the left 2. I ended up at 3. And then I went to the right 4. So it's like the areas under the velocities could have been added together to give you displacement. Can your calculator find the area under the velocity? Yes, using math 9 or using y equals and second calc 7. I don't know what x of 3 is. I do know what x of 0 is, and my calculator can quickly and easily find my displacement, my area under my velocity. That's it. Where does this come from? This comes from our formula. This comes from the way I introduced this whole concept of displacement, how there are 2 ways to find displacement. Using a calculator, your calculator can find an accumulation. What can you do? Take an antiderivative, subtract positions. Ready? I could solve this for x of b by adding x of a. And all of a sudden, I have a new formula. My unknown position equals my known position plus my displacement between the two. You may use your calculator. Please get 12. X of 0 is 3. Ready? Do I have to show you? I feel like you guys are lost, but I'm giving you gold. This has been the best one by far. Yesterday, I was like, man, I'm not doing a good job. X of 0 is 3 plus integral from 0 to 3. Accumulate my velocity of t squared from 0 to 3. Accumulate my velocity from 0 to 3 because I know that's going to be my displacement. Boom, you get 12. Now, would you use this method if I said this is a no calculator problem? No, because like this isn't very efficient having to take the antiderivative, plug in 3. It's like I'd rather find C. But we are about to see some new things, guys. Skip this problem, go to this problem. We are about to be given equations that we are not able to take the antiderivative of. This would be strictly a calculator problem. And there will be calculator portions on quizzes and tests from now on. The calculator is now going to be used a lot. Because the calculator can accumulate. We can't. We can take antiderivatives, but we can't accumulate. So, I can't take the antiderivative of 6 times t squared. You might think you can. You might think, oh, yeah, isn't it negative 6 cos 1/3 t cubed? No, it's not. So, it's wrong. Like, try. You get it wrong. But I'm still going to be asking you, hey, where am I? Where's the dude? Dude started at position 3. Where's the dude at position 2? You will not be able to take the antiderivative. You will not be able to find C. You will only be able to use your calculator's ability to find areas to accumulate velocities, which are displacement. It's how far I ended up versus where I started. I will take that displacement and add it to my known position. And that'll give me my future position. Okay? Where did the dude end up? That's the second. Go ahead. From now on, calculator sections, boom, you can find the area quickly. No calculator sections. Oh, I'm going to have to take the antiderivative. I'm going to have to find the change in the position. I'm going to have to find C. Yeah, I have to start somewhere plus my displacement. The area under my velocity is just how far I've traveled. It does not take into account where I started. It's a weird graph, but what does this show you? This is important. 6 sine t squared from 0 to 2 is probably the best, right? Does it look like this? Now, what is this? Velocity. The area, when the velocity is positive, is telling me how far I've gone right. The area, when my velocity is negative, is telling me how far I've gone left. If you combine those areas, it'll just tell you your displacement, the change in your position. Second calc, your friend number 7, 0 to 2. okay, I'm going to the right a bunch, but then I'm going back to the left. What happens? I will end up 4.828 away from where I started. It's important to understand that this is not a position. This is how far I ended versus where I started. I know where I started. I started at a position of 3. I add that. I now know where I ended. 7.828. Now, what's important is understanding, and we will do more analysis in the future of, okay, the dude started at a position of 3. The dude's velocity is positive until this value. In the future, we will find that value. On your homework, you will find that value. If you found the area from 0 to that value, you'll figure out how far you've traveled right. And then the dude has a negative velocity. He goes to the left. If you found the area from here to the end, you'll figure out how far you've traveled left. Overall, his displacement, his change in position, was 4.828 from where he started, which is why he ended up at 7.828. Okay? Skip this. Now we got something fun. Again, I still can't take the antiderivative of this. So I can't do the whole x of t and then find c, which means I can't find c when I have 5, 6, and then I can't plug in 0. But we can still use our friends. But here's the problem. I have x of 5 equals 6, and I'm trying to find x of 0. This is like before. All right, well, start with this. Find the area under velocity. Find the accumulation of my velocity from 0 to 5. Go. You got to do this quickly. Don't leave when the bell rings, because we got to do this last problem. I'm going to go on the home screen and do this. Make sure your calculator is always in rating mode. All right. What does this tell me? Tell your neighbor. This tells me that I ended up displacing 4.307 units to the left from my 0th second to my 5th second. What position am I given? My 5th second is 6. How can I find my 0th second? I will add a positive, because I will have to go to the right to figure out where I started at my 0th second. Watch this, guys. It's the same. You just figured it out naturally. It's the same as starting with my new kind of equation. My unknown in the future equals my known in the past plus my displacement. But what do I have? 6 equals x of 0, I don't know, plus negative 4.307. Add 4.307 to both sides, just like you suspected. It is very important to do your homework. Don't leave during lesson. Wait till after the quiz before the lesson.